I hope you had a great time here at Vox Days in CERN. Lots of interesting stuff on the agenda, and now we're going to talk about the past, the present, and the future of cross-site request forgery. And well, I can tell you, if you start writing talk titles that start with the past, then you kind of get to feel old a bit and stuff like that. But the goal for today is to talk about cross-site request forgery, which is kind of a mouthful, so it's abbreviated as CSRF, CSRF, a lot easier to talk about. That's one thing. We're going to talk about the past, like old applications, stuff you probably still have lying around, but that aren't cool anymore. And then we'll talk a bit about API-based applications, what it means, and mainly how to defend your applications against cross-site request forgery. And to do that, I need to start with explaining CSRF. I need to start with trying to make clear what CSRF is, what the problem is, where it comes from, and then we can talk about defenses. So I'm going to start by explaining the problem using Retrograde. Retrograde is my training application, so I use this for training and demo purposes, and it's a restaurant review app. So very familiar, everybody kind of knows how that works. You have restaurants and you have reviews, and that's pretty much it. So what's the idea? The idea in this application is that the user has a browser, they are accessing the application, and we keep track of the user's authentication state with a cookie. That's kind of the premise for cross-site request forgery. So at some point in time, you're going to log in, username, password, multi-factor authentication, whatever hoops you have to jump through to make this happen, you authenticate as user. And the application is going to give you a cookie, and that cookie is going to keep track of your authentication state. Purposely being very vague here, authentication state. Why? Because there can be a server-side session with a session ID, like the old thing. But it can also be like a token that is stored in a cookie, which would be like a new thing, maybe. Depends a bit on what you call what. But it doesn't really matter what it is. What matters is the transport mechanism are cookies. So the browser will accept the cookie, store the cookie in the cookie jar, literal browser terminology, I'm not making this up, a cookie jar in the cookie, and whenever a new request goes out to this host, app.retrograde.com, the browser will see that request, attach the cookie, send it out, and the server will process that. The server will use the value in the cookie to identify who you are, like, oh yeah, that's Philippe from 2 minutes ago, and create a review in my name, and so on and so on. And essentially everybody is happy in this little scenario. That is normal application behavior. Whenever this happens in an application, i.e. using cookies to keep track of who the user is, a session or a token or whatever you're doing with cookies. Once that premise is there, you are a potential victim, or the application is a potential target for cross-site request forgery. And cross-site request forgery is an attack where the attacker is going to send an identical request as the user has done from within the user's browser. So very concretely, if I would be the attacker and you would be the victim here, you would visit one of my evil web pages, and that evil web page is going to send a request to this backend. And for my training purposes, my evil website is maliciousfood.com. And you can see here, there's asparagus trying to trap you some way, whatever. Not very relevant here. How do you get there? Well, I can send you a link. I can tell you like, oh, go here. I have to grab a copy of the slides, and everybody's like, oh yeah, let's do that. Or some friends of you post something on Facebook, or somebody hacks their account and they post something on Facebook and you follow the link, and whatever you end up at some site, which is obviously not going to announce its maliciousness, but it's going to be malicious in nature. And in the background, that site is going to send a request. It's going to load a hidden iframe, and in the hidden iframe, it's going to include a form, and the form will contain here some parameters like a title and content, and the form will be submitted to app.retrograde.com. And the moment this request leaves the browser of the user here has that cookie associated with the target application. It's going to be like, oh, hold on, I'm going to slap the cookie on this request so that the server knows who I am, and the server will get a request to create a review. And the request, if you look here, looks identical to the one we had in the legitimate scenario. And the server is somewhat vulnerable. The application doesn't really know about CSRF. It's like, yeah, that looks good enough. Oh, that's Philippe from 2 minutes ago. Bam, create a review. And in this case, we're not very happy. The attacker might be, but we are not. And that is cross-site request forgery in action. All right. Let me show you that. I'll have a couple of demos throughout the talk. So let me show you how that works so that we have a good idea, and then we'll build on that in the future when we talk about defenses. Unsurprisingly, I have a restaurant review application as a demo, and when we log into the restaurant review application with a username and a not so secure password, we will get a cookie here. It's a JSession ID. Simple server-side session, can be anything like I said before, and we can now see reviews and create reviews. We can add a review, very useful data here. And submit that review, and we can go back to the list, and you can see that the list or the review is now created in user's name. Very simple, very straightforward. All right, what are we going to do? Well, we're going to launch an attack, and the attacker page is, let me cheat and copy a URL, is hosted on malicious food. So somebody sends you a link, you follow that, you open the page, and you get some images of malicious food. However, in the background, the attacker has a malicious frame, so there's a small text at the bottom to show the malicious nature, and the malicious frame is actually trying to execute a CSRF attack. That's essentially what's going on. In this case, it's not configured correctly, so it's not working, but that's how the attacker would launch the attack. To make it work, here's a form, and we have to point it to the right location, the endpoint to create a new review, and if you would inspect as the attacker, you would be a user of the application, you can go here and inspect where we send a request to create a review. That should be a post here, new review something something. So if you would take this as the attacker, drop it in our malicious page, save it, that should create a review, name test, no, that's not going to work. We should take the correct input fields right here. That's a leftover from another demo. We have a title and a content, and now we can create a new review at this endpoint. So let's see if this actually works. We go to our victim browser. We're the user, we're the victim. We end up on this malicious page, and you should be able to see in a network that we sent a post request right here to create a review, and it says 200 OK. Now, as a user, if you would go back to the application and show the reviews again, you can now see that we have a new review that has appeared from the CSRF attack. That's essentially cross-site request forgery in action. The attacker is triggering a request from the browser, and the browser attaches the cookie, and the server becomes a bit vulnerable. That's essentially what's going on right here. All right. Brings us to takeaway number 1. This is a traditional server-side application, GSP pages and whatnot. Traditional server-side applications are vulnerable to cross-site request forgery. This should not be news. Well, sounds a bit arrogant here, but this is something we've known about for like 15 or 20 years. CSRF has been around for a long time, has been part of the OWASP security top 10 for a long time, and so on and so on. And actually, it's such a big problem that a lot of server-side frameworks have built-in support to stop CSRF attacks. For example, Spring Security has built-in support to try and defend against these CSRF-based vulnerabilities. In essence, whenever you have a server-side application relying on cookies, you might be vulnerable to CSRF, and you have to take explicit action to stop that from happening. That's essentially my introduction to cross-site request forgery. All right. Small word about myself. I'm Philippe de Ryck. I'm from Belgium, and I'm a security expert, in case you were wondering. That's why I talk about security. And what I do in my day-to-day job, well, I speak at conferences quite a bit, but I also do trainings and workshops for developers, where we dive deep into security topics, help them understand how things work, and of course, how to build secure applications. I also provide consulting on specific security topics to help people understand what's going on, make decisions, and so on and so on. All right, I'm a Google developer expert and Auth0 ambassador, which means these companies recognize the work I'm doing in the community and the stuff I'm talking about. It's just a recognition and part of their DevRel program. I don't work for Google or Auth0. They just send me free swag every now and then, and I'm happy, and I mention them, and they're happy, and that's our symbiotic relationship. Now, finally, I organize SecOpDev in Belgium, a week-long course on application security, where we bring people from all over the world to talk about security. A bit like this, but maybe a bit smaller and a bit more focused on security. So if you're ever interested to visit Belgium, that would be the perfect opportunity. All right. Housekeeping. You can find a copy of the slides on my website, so you can grab them by scanning the QR code here, which will not take you to a malicious page, I promise. And otherwise, you can just look them up on LinkedIn or Mastodon. I'm easy to find, and the slides are also pretty easy to find as well. Just to give you an example, this is how easy it is to end up on a malicious page. Just scan whatever you find, and off we go. Now, let's make this useful. more useful than it has maybe already been. Let's talk about stopping CSRF, because that's what I'm really interested in. Attacking stuff is cool and fun, but stopping things, stopping attacks, that's the real effort that we have to take here. And like I said, CSRF is not a new problem, and we've had a solution for a long time, and that solution is known as synchronizer tokens. And it basically works as this. It's really hard for the server-side application to detect legitimate from illegitimate requests because there's no difference. The only difference is intent, like did the user really want to send this, or did somebody else trick the browser into sending this? And there's very hard to distinguish between those two types of requests. So what can we do? The solution is, what if we hide a secret in a legitimate request? And only the application has that secret, and then if we find a request without a secret, we can silently discard it or very verbosely discard it and get it out. And this works with generating for a user session. We generate like a secret CSRF token and we embed this in a form. Server-side applications, GSP pages, forms, very easy, very simple. And whenever the form is submitted, that secret CSRF token will be part of the data, and the server will check it like, is this the token I gave to Philippe? Like, oh yeah, it is, good. This must be legitimate, must be coming from my own form submissions. Why does this work? Because when the attacker tries to do the same thing, the attacker tries to launch the attack just like before, sends a request just like before, the browser adds the cookie just like before, and the backend is going to be like, hey, where's that secret? And the attacker can't read it because the secret is in your browser on your application of retrograde, and there's no way for the attacker from malicious food to inspect pages from another application in the browser of a user. Impossible. Of course, they can come to your house and beat you with a pipe and then steal whatever they want, but in that case, CSRF is probably not your biggest worry. You should think about other things. But in this case, the attacker doesn't have the secret, so the server can be like, you don't know the secret, go away. And that's essentially why synchronizer tokens are a good defense against cross-site request forgery. And this pattern has been implemented by default, I think the first time in Ruby on Rails, and has made its way in a couple of different frameworks as well. This is good CSRF defense. This works, awesome, works really well, has some scalability challenges, but there's a variation called double submit cookies where you can push the load of keeping track of the secret to the browser and so on. Also a good pattern. This works quite well. The problem is, it only works if you implement it. It only works if you heard someone talk about CSRF, if you took the effort of implementing this in your state-changing request like form submissions, and that is not always the case. That's not something that is always done. It's sometimes forgotten or omitted, which causes CSRF vulnerabilities and so on and so on. And that's when people looked at this and they said, like, actually, this is kind of a stupid problem to have. Because this is created by browsers back in the day when we didn't know any better, that just add cookies on all outgoing requests and things will work out, hopefully, and they don't always work out. And that's when people came up with, like, what if we can just fix that behavior using same-site cookies? And same-site cookies, well, if you ask ChatGPT, it's not very useful. It creates some weird image about same-site cookies. Also includes a cookie here without any face, which is really scary, by the way. I don't know what's going on. Seriously. So what are same-site cookies? Same-site cookies, the property is a flag you can add to a cookie. And you can tell the browser, this cookie is intended for same-site requests only. And you use it like this. So you set a cookie when the user logs in, and you add same-site to it, right there. Framework support this, it's just a configuration option, bam, and you're done. And this tells the browser that this is for same-site requests. So whenever there's a cross-site request, like in cross-site request forgery, that's going to be a different site, and the browser will be like, hold on, no. This cookie is for same-site only, I'm not going to attach it to cross-site requests. And that's essentially what happens. So the attacker sends a request, the browser sees it sees the request leaving, it's like at the cookie store, like, I have a cookie, but it's same site, so I'm not going to attach it because this is a cross-site request, and the application will have no idea who you are, and the problem goes away. Awesome. Now a site, just for the record, a site is defined as the ETLD plus 1. So in this case, ETLD is the .com, the .co.uk, the .whatever, and then you go one level further down, and that's the retrograde, well, in this case, retrograde, yes. So the site here is retrograde.com and maliciousfood.com cross-site, because they're different. That's essentially what this means. All right? Good. Same-site cookies solve CSRF. Awesome. It's really that simple. There's two configuration options like lax and strict. It's not really that important. Adding same-site to a cookie will solve CSRF problems. Awesome. Now, you still need to do this. So it makes it easier to solve it, but it still requires active effort from developers. And that's when people at Google said, actually did my PhD on this topic as well, and that's when people at Google said, like, you know what if we just made this the default? What if all cookies are same-site cookies? Unless you really don't want to, then you can turn it off. That's what Chrome did in 2020. They added the same-site behavior as the default cookie behavior. So whenever you set a cookie in Chrome, the browser is going to treat it as same-site unless you tell the browser, like, hey man, I know about this same-site, cross-site stuff, make this a normal cookie. But otherwise, it's going to be a same-site cookie by default when you're using Chrome. Let's see what that means in practice. First of all, it means that I'm a cheating bastard, because if you look at the cookies, this is a cross-site request, and Chrome does this by default, and this is Chrome. Like, why does this even work? It's because I actually set same-site to none, to mimic the behavior of old cookies. Otherwise, this would not have worked in Chrome. So yeah, that's one way of cheating in the browser. So what you're supposed to do is actually just enable same-site cookies. We can do that. Like I said, it's a configuration property. We can set same-site to lax. That's the most permissive configuration option. The details are not that important. And this is enough to stop. Let me show you. Let me clear the old cookies. Yeah, they're gone. So let's log in again. We're logged in. And let us now reload the attack. You can see that same-site is set to lax here, and you should be able to see that this post request failed with a 403 now. So our attack from before, we haven't changed the attack. The only thing we changed is cookie behavior. We set it to lax, and all of a sudden there's no cookie. The application doesn't know who we are, and the problem goes away. And that's the default behavior in Chrome. All right, that's awesome, if you ask me. Takeaway here, Chrome handles cookies as same-site by default. Other browsers do not. Firefox has their own idea of compartmentalizing cookies and so on. Chrome is the only one that does it, so you still need to set it to cover the other 5% of your users, but the other 95% using Chrome will be covered. That's essentially what this means. Good defense. All right. All good? Nice and comfy in the beautiful chairs here. That's good. So far, I've been talking about old applications. Some of you may be like, yeah, that's what I've been doing for 25 years. And some of you may be like, dude, come on. What about APIs? We build APIs these days. We don't build server-side applications. Well, for APIs, the story is remarkably similar. If you have an API, I created a new slide here. I changed my icon with an API icon, and that's it. If your API, seriously, that's it. If your API is accepting or keeping track of user authentication state with cookies, which a lot of APIs actually do, and there's nothing wrong with that. Well, maybe that's a discussion for a different time, but I don't think there's anything wrong with that. Then the legitimate behavior is going to be a submission, a post request with JSON data. It's not a form submission, but it's JSON data. The cookie is there, and the API knows who you are, and everything just works as it should. All right, and then the attacker comes around. And what changes here? Well, nothing, really. Because you can manipulate the data in a form, which usually is like key equals value, something, something. You can manipulate the data to make it look like JSON. So the attacker can be like, I'm going to create a form, and I'm going to name my values in the form very creatively, and what will result in that submission is a JSON-based call to an API endpoint with a cookie. An API figures out who you are, creates a review in your name. That's one way of carrying out that CSRF attack. A more modern attacker might figure out that you can send the same request from JavaScript, right? Instead of having to massage the data in a form to make it work, you can actually send the same request with fetch, browser-based API to send requests, and you can just provide JSON data there. No need to do weird tricks to make it happen, and you can send a request to the API and carry out a CSRF attack. That's the story for APIs. It's basically the same as it is for server-side applications like we had in the good old days. Well, good in the old days. This happens in practice. Here's an example from a dating app OkCupid, which had exactly a vulnerability like this, allowing people to send messages through a CSRF-based request to an API, just to show you that this is an actual thing in the real world. And I can actually show you how to carry out such an attack in practice as well. To do that, I don't really have to change much because the application is also an API-based application. So if we log in here, we don't enable the legacy, then we're now an API-based application, and we can add a review as the user. And you should be able to see that this is now a post request with JSON data. Very simple, very straightforward. How do we carry out this attack this attack against the API? Well, we can do the same. Let me show you. In our frame-based approach, we can use this form right here. It's almost like real development with ChatGPT, just copy, paste, and it should work. Here's the trick. You can use this as the name of a field. The browser will add an equal sign in between the key and the value, the name and the value. So the name is this, and the value is that, and together that will make an object that actually parses as JSON. That's the weird trick you can use in forms, and you add text/plain as the encoding to tell the browser to not encode special characters in like the form-based representation. All right, save it. The endpoint is now an API endpoint as well. We go here, we launch our attack, which is not going to work, sorry, because we have to enable our same-site cookie or disable same-site cookies again. My bad. Always good when I think about this before showing that it doesn't work. All right, same-site is turned off, so this attack should work in practice now. Load it, and you can see the request going out here. It's a post request to an API endpoint, and Chrome even parses this as JSON data. And you can see that it's actually the name of a form field here equals the value of a form field, and it's valid JSON. Seriously, this works in practice. We can also do a fetch-based attack. Let me show you. Let's comment out the frame and enable a fetch-based attack. It's a bit cleaner here. We have a URL, we have some data, and we just send a fetch request, and off it goes. Let me show you that that one works as well. Clear this, reload this, and wait for 2 seconds, and there we go. That's the request going out, a fetch-based CSRF request. Good. Well, not good, but you kind of get the idea. How can we fix this? Well, same-site cookies, right? If we would have used same-site cookies or not turned it off in Chrome, then the attack is thwarted. So let me show you real quick, because it matters for the next part. Same-site lags, attacker comes around, carries out the attack, and we get a 403 forbidden. So same-site cookies to the rescue, also for our API-based applications. I also have that on the slide. So same-site cookies prevent CSRF against APIs, and the takeaway here is that if your API relies on a cookie to keep track of who the user is, which is a valid pattern, you need to think about CSRF. And same-site cookies are a good defense against cross-site request forgery. And if you're thinking like, yeah, dude, but I don't build APIs with cookies, well, if you're doing OAuth in an API-based world, then the best practice for dealing with OAuth in frontends is to not do it in the frontend, but use a backend for frontend, a BFF, which is an API using cookies to keep track of OAuth tokens. Details are way too difficult to explain here, but look it up online. I've done talks about that topic as well, or just grab me right after the talk if you want to chat about this. But cookie-based APIs exist, they're not uncommon, and they're even a best practice in the world of OAuth. All right, just to make sure that this is relevant stuff. Where does it leave us? Well, it leaves us at the takeaway that same-site cookies are awesome. They help stop CSRF. So I wasted 30 minutes of your time to talk about a non-existing problem, which is awesome, right? Perfect after lunch. Everybody's like, oh, thank you. That was good. You didn't miss anything if you just slept through the first part of the presentation. If if you did sleep, now is the time to wake up, because things will get more interesting really fast. Same-site cookies are awesome to stop cross-site request forgery. But what about cross-origin, but same-site request forgery? Which doesn't really sound good, but the problem is, what if the attacker can launch the attack from a subdomain within your site? If you're restograde.com and the attacker can use malicious.restograde.com for some reason, then cookies will be same site, the request will be same site, cookies same site, they're attached, and we have a problem again. So let's take a look at that exact problem. I did some preparation, so the only thing I have to do here is change my malicious food to malicious.restograde.com, same page, and the request goes out, and it succeeds right here. It goes out, we have same-site cookies enabled from before, and it just works. This is Cross-Origin Request Forgery, or CORF if you want the ugly acronym for that. I don't know any better way to pronounce it, so it's going to be Cross-Origin Request Forgery. Yeah, that's not good, in case you're wondering. That's the red color on the previous slide, means not good. I'm sure you're wondering, like, seriously, dude, why would the attacker ever run something on a subdomain? Like, we don't just give them out to attackers. That makes no sense at all. So how do we get there? How does that happen? Well, it turns out that a lot of people's DNS services are not very well configured. And that you have a lot of CNAME, which are aliases, basically pointers, like, hey, app.restograde.com points to this DNS name, which is something.azure websites.whatever, or something on AWS, or something on, I don't know, Cloudflare, and so on and so on. And it turns out that the internet is full of these dangling DNS pointers, something you've used in the past, and then you destroyed the actual property, like old.restograde.com, no longer exists, and the attacker will find that DNS entry somewhere, and it's like, oh, this points to there. And they'll just register that old property again on AWS or Google or whatever, and all of a sudden, the attacker can host content here on a cloud platform or on a specific IP address which is accessible through your DNS records, old.restograde.com. And before you say, like, yeah, come on, that doesn't happen. Oh, yes, it does. It really, really does. This is a real problem. So CSRF is dead. That's good. Same-site cookies, awesome. Long live CORF, Cross-Origin Request Forgery. Same site, but Cross-Origin Request Forgery. And seriously, I know this sounds like I'm just making stuff up to fill 45 minutes at Fox Day CERN, but it's really, really not the case. Microsoft has been bitten a lot by dangling subdomains, like just forgotten pointers. And I can guarantee that if you go look at your DNS configurations, you'll find CNAMEs that you're no longer using. Trust me, they're there. And this happens in real applications as well. And here's a story from Grafana, kind of a very important open source framework or application that was vulnerable to this because their APIs could be attacked. So if you're running Grafana on grafana.restograde.com and somebody gets control of our subdomain, they could be able to control or attack this system, take it over, and escalate the attack from there. So this is a real problem that happens in the real world. And the real question is, why does that even work, and how can we stop it? And to do that, I'm going to go back to my demo, and I'm going to show you, because this is not a straight-up vulnerability that is always possible. It requires your API to be a bit too lenient. It requires your API to be like, yeah, whatever. And if your API is like, it's all good, then the attacker may launch the attack, and you may be in trouble, but we can solve it. That's essentially what we're going to talk about in the last part here. OkCupid had the same problem, by the way. Let me show you first. Here's our successful attack. And if you look at this, the data is JSON. So it parses as JSON, it's really true. But if you look at the way we sent that request, you can see that the content type is text/plain. And that's a very important detail, because it means that the browser will send this request without asking questions. The browser is like, I'll send it. Because you can submit the same thing with a form. I showed you the form submission from before. Form also uses the encoding text/plain, and that's why the browser allows such a request. The first problem is our API should have never accepted this. Our API is misconfigured in a sense that it doesn't force a request to have the content type application/JSON. That's a mistake. If the API would have done that, if you would have added consumes application/JSON, then Spring, in this case, would enforce that content type. We didn't, and that essentially causes the issue. So let me show you that this works. Let's log in again, because we need that active session, and then launch the attack. You will now see that the attack comes back with a 415, which means unsupported media type. Now, our server-side framework is like, hey, you said that this accepts application/JSON. I don't care if it looks like JSON. I don't care if it parses as JSON. I care about the content type. And only if the content type says that this is JSON, I will accept it. Otherwise, go away. That's essentially what the application is doing here. That's very important. Why? Because the attacker can't really change this. The attacker can, of course. I mean, it's not hard. It's just, well, it is hard if you can't type like me, but it's not hard to do it in practice. So you write application/JSON. And then you send the request in the browser. And guess what the browser will do here? The browser will send the request with text/plain as a content type. And you're like, what? Why are you doing that? Seriously, this is going to go deep down the rabbit hole. Why is this text/plain? Well, because we're telling the browser to pretend that CORS doesn't exist. CORS, Cross-Origin Resource Sharing, a new feature. It's from 2009, so it's not new anymore, but a specific feature that enables cross-origin requests in the browser from JavaScript. Because in 2008, this wasn't possible. If you tried this in 2008, the browser was like, no. I want to send a request to app.restofgate.com. The browser was no. Unless you are actually running something on app.restofgate.com, the browser simply refuses. And with adding the mode no CORS, we tell the browser, let's pretend it's 2008 and it doesn't exist. Well, in 2008, you couldn't send this request except with a form and text/plain as a content type. So when we send this, the browser is like, yeah, it's 2008. I'm going to pretend that you didn't write that and just send the request with text/plain. And the application is like, not good enough, go away. So now you're thinking like, yeah, but what if we didn't pretend it was 2008? Well, in that case, we do it like this. And now the browser is like, of course you can send cross-origin requests. And yes, you can send custom headers all you want, but, and this but is very important, when you do that, I'm going to ask permission first. Because the server may not be aware that this is a new feature in the browsers. And the browser is going to send a options request first. This is CORS in action. And the browser is basically asking the server like, hey man, I don't know if you've been updated since 2008, but I want to check if you're aware that I can send this cross-origin request with a custom content type header. And unless the server says like, of course I know about that, and yes, you, malicious.restofgate.com, are allowed to do that, unless the server says exactly that, the browser is like, okay, I will not send you the request. And you can see that here. The browser is asking permission to send a custom content type header with a post request coming from malicious.restofgate.com. And the only way that the server will respond to this is if you have a CORS policy configured that says, I want to accept requests from malicious.restofgate.com, which you obviously will not have in your, well, there's ways you can screw that up, but that's a story for a different time. And the server, the response here is like, I don't know. And the browser is like, oh, sorry, I asked. And that's why you see the error here. The browser did not send this request. The browser never sent the post request because the server did not agree to accept it. And that's CORS in action. And that's why the content type matters. And that's why the vulnerabilities in OkCupid and Grafana and a whole bunch of other applications, they had that content type misconfiguration. That's essentially what's going on. CORS, cross-origin resource sharing, can be used as a CSRF defense and even a cross-origin request forgery defense. That's essentially the very important takeaway. Now, we have to dig a little bit deeper, just a little bit. This works perfectly fine for all your endpoints that have a content type. Because you can say application/JSON and the browser will have to ask permission and you're good. But there are cases where you actually don't want to accept JSON but text/plain. They're weird, but they exist. Or cases where you don't have a body. Like a bodiless post, a logout is a very good example, but there are some others, like weird scenarios. And if you don't have a body, you don't have a content type, and you don't have something to enforce, and you have cross-origin or cross-site request forgery again. So there's a trick you can use to force every request from being a course protected request, and that's by asking the client to send a custom header. And I have a CSRF header enforcer here, really awesome naming. And we just require every request to have an X CSRF header, or Foxday CERN is awesome header, or whatever you can think of. I mean, it doesn't really matter. And we force this to be present, like this. And we can run this again, log in, all good. The attack, well, sorry. I should have made my application vulnerable again to really show this in action. So we'll remove our good coding and go back to the bad coding and reestablish a session. All right, if we launch our attack like before, tech/play, no course should be enough. If we launch it like this from our SameSite but cross-origin source, you can see a 400, which is essentially what's going on. The response here, well, no response, but the 400 bad request is because of the CSRF header thingy. And the attacker can send that header, but guess what you couldn't do in 2008, what you can't do with a form submission, send custom header. So if the attacker wants to add a header here, like X CSRF 1, and you want to send it again, guess what the browser is going to do? It's like, hold on, before 2008, we can't send such a request, so I'm not going to include that header. So the header is not included here. And if you enable the post-2009 mode, like course, which every browser does support today, the browser is going to be like, yes, I can send it, but only if I get permission to do that. And you'll get, always check the demos, you get the actual options, and in the options request, you'll see the browser asking like, hey man, can I send you this XCSRF header? And the server is going to be like, I don't know. And the browser is not going to do it. So it says request headers XCSRF, and that's why this works, because only when the server says like, yes, I want stuff from malicious.restocate.com, the request is not going to go through. Now, why does this work with a legitimate application? Because I already implemented support for that. Well, we should be able to see it here as well. Yes, I implemented support for this. First of all, this is same origin, restocate.com to restocate.com. There's no different origin, so within the origin you can do whatever you want. Has always been the case, even before 2009, before core support. And the application sends the header, so there's no pre-flight. You send the header, the server is happy, and in essence, everybody is happy. Except maybe you, because this took us really deep into CSRF and course. Let me dig ourselves out of the rabbit hole. CSRF is solved by same-site cookies. CORF, Cross-Origin Request Forgery, in this case for APIs, is solved by using course as a defense, by basically requiring requests to fall under course protections, requiring a cross-origin request to have a pre-flight, allowing the server to say like, no, go away, I don't want that request. And that's how you can use course as that CSRF defense. Content types should be enough, but to be honest, the easiest solution is just add that custom header and the problem just goes away. You can forget about this and you're done. And I mentioned OAuths and BFFs and all of that setup. There's a BFF library built by a friend of mine that actually does exactly this pattern to stop CSRF out of the box. So it's if you're using Duende BFF libraries, then it's basically solved that problem. All right, now digging myself out of the hole on CSRF and course. I have a flow chart to help you decide what you need to do. If your application is the only one running in a site, like if you deploy your app on restocate.com and you have no subdomains and you don't run anything else on the restocate.com, easy, same-site cookies, perfect. If that's the case, same-site cookies are a really good defense because there's no cross-origin request forgery because there's nothing else in that origin, only you. Good. If you do have multiple applications in a site, think about maybe changing that, but that's not an option here. So that's one out-of-the-box solution. But the next question is your application a traditional server-side application? Like, do you rely on form submissions and form content types and so on? Because if you do, things are tricky, and you kind of need to use synchronizer tokens because you can't rely on course as a defense. So in that case, synchronize it. That's why I talked about the old defense with the secret in the form submissions and so on, because it's still relevant to stop cross-origin request forgery. Now, if you're building cool applications and it's API based, then you can use CORS as a defense, using the guidelines I told you before of requiring the content type and the custom header and so on. And if you're building anything else, well, I really don't know anymore. So maybe talk to me after the session to see what the hell you're doing. If you're running a mainframe, then you probably don't have cross-site requests anyway. So you're probably good. But seriously, key takeaways. Final slide here. CSRF matters when you rely on cookies to propagate authentication state, when cookies are the transport mechanism. If you're using a custom header with a token in the authorization header, then CSRF is not a problem. You can forget about that, but cookies are more common than you might think, so keep that in mind. SameSite cookies mitigate CSRF, but not cross-origin request forgery. And for the final part, at least for APIs, you need CORS to protect against cross-star request forgery. That will basically solve that problem once and for all. I hope this was useful. Thank you for being here. Enjoy the rest of the conference, and I have a bit of time after the talk to answer some questions or discuss whatever you want. Thank you. You're dismissed. No, if you want to ask a question in group, let's just come up here. It's going to be a bit easier to answer questions. So if you have anything specific, don't hesitate to ask.